In video 1, we learned that an event is a set of outcomes of a random experiment, and that if the outcome of a random experiment is contained in an event, that we say the event has occurred. In this video, we are going to define what we mean by the probability of an event. We'll use the notation P of A to represent the probability that event A occurs. And this can be thought of as the chance or likelihood that event A occurs. And one way that we sort of develop the idea of probability is by looking at something like, for instance, if we consider repeating the random experiment of flipping a coin, and we let A be the event that we get heads, if we call the number of flips n, and the number of times that A occurs n of A, then we can calculate the relative frequency of event A occurring by taking n of A and dividing by n. This is just the proportion of times that we get head in our coin flips. And I'm going to take a look at a simulation of this. So let's take a quick peek here. So this is an applet online that shows how often we get heads is 50%, and if we make a guess and see, okay, how often will we correctly guess? This is supposed to be looking to see if we're psychic, but what we can do is just look at how often they're heads if we always click heads. So let's see. Okay, the first one was tails, so that was 0% correct, and keep going. Okay, now I got 50% correct because that one was a heads. Now I'm up, up, down, up, up, down. I can see my overall relative frequency of heads is pretty unstable when I have a small number of flips. But as I have a larger and larger number of trials here, more flips, it's starting to become much more stable. It's fluctuating less and less. As I say that, of course, it fluctuates more just by chance. But I still have a relatively small number of flips here. Keep going. And eventually, this is going to level off. Keep going. And it's getting closer and closer to 50%, which is that. And then it's becoming very stable. Okay, so we can think of probability as sort of the long-term relative frequency. If we were to increase the number of trials without bound, so go out to infinite number of trials, just keep doing this forever, that long-term relative frequency of the event occurring can be thought of as the probability that the event will occur. So now we have this idea that the probability is the long-term relative frequency of an event occurring. And if we want to define that more formally, mathematically speaking, probability is a real valued set function P that assigns to each event A in the sample space S a number, which we call P of A, which is the probability of event A, such that the following hold. A, the probability of any event A must be non-negative. So P of A has to be greater than or equal to 0. The second property is that the probability of the entire sample space is going to be equal to 1. Something has to happen. We have all the possible outcomes, then the probability of the sample space is equal to 1. This makes good sense. The third property is that if we have mutually exclusive events, that the probability of their union can be found by adding up the probabilities. So if we have a finite number of mutually exclusive events, then we can add up their probabilities. And if we have an infinite number, we can take this infinite sum and add the probabilities to find the probability of a union. So if we have mutually exclusive events, we can find the probability of the union by adding up the probabilities of the individual events. This is the basic idea here. Now, there are a couple of ways that probabilities are assigned. There's an approach called classical probability that is used when we have equally likely outcomes. For instance, when we're rolling a die, each of the 6 sides are equally likely to come up, or if we're flipping a coin, we're equally likely to have heads or tails. When we have these types of situations, we can assign the probability to an event A by counting the number of the possible outcomes that are contained in A and then dividing by the total number of outcomes in the sample space. So for instance, with our 6-sided die, we know that the sample space is the numbers 1, 2, 3, 4, 5, and 6 that can land heads up, face up. A from our last video was the event that we had an even number, and that consisted of the set 2, 4, and 6. The probability of having an even number, P of A, is equal to 3 divided by 6, because there are 3 possible outcomes in A, and there are 6 possible outcomes in the total sample space. So the chance of getting an even is 3 out of 6, which is 0.5. Now, when we don't have equally likely outcomes, we cannot do this. In that case, we often use what's called empirical probability. And we base our probability of an event A on the relative frequency with which event A occurs. So, for instance, if we're looking at moviegoers and whether or not they buy popcorn, our sample space is going to consist of a set where they either buy popcorn or they don't buy popcorn. If we're interested in the event that they do buy popcorn, and we want to try to find the probability that a randomly selected moviegoer will buy popcorn, we might observe 200 moviegoers. We see that 65 of them bought popcorn, and so we could calculate our probability, P of A, by taking the number that bought popcorn divided by the total number of moviegoers. It would be 0.325. So this is the empirical method of assigning probabilities, just based on relative frequency. I always want to mention some of these theorems that are in the first lesson. There are 6 fundamental theorems here that are going to be extremely useful as we continue to work with probability. You don't need to necessarily memorize these theorems, but it is important that you understand the concepts behind these theorems and that you take the time to work through the proofs of them. Most of them the proofs are in the book, so you can take a look at the steps, and if you find that there's one of them that you're having trouble following, you can post something onto the help board, on the discussion board, and we will post a video that will walk through the proof. So the first theorem tells us that the probability of an event A is equal to 1 minus the probability of its complement. The second theorem tells us that the probability of the empty set is equal to 0. The third tells us that if A is a subset of B, then the probability of A has to be less than or equal to the probability of B. Our fourth theorem tells us that the probability of A is less than or equal to 1. And this makes sense because the probability of the sample space has to be equal to 1, and any event A has to be a subset of the sample space, so it has to be less than or equal to 1. Theorem 1.1.5 tells us that if we have any two events A and B, if we want to find the probability of the union of A and B, then we take the probability of A plus the probability of B, and we subtract the probability of their intersection. And then our final theorem, 1.1-6, extends that to more than two events. If we wanted to find the probability of A union B union C, we'd add up all of their individual probabilities, probability of A plus probability of B plus probability of C, subtract off all the intersections, subtract off the probability of A intersect B minus probability of A intersect C minus probability of B intersect C, and then add in where they all three intersect. So that brings us to the end of this video. As I say, I do recommend that you look through the proofs of these theorems in the book and make sure that you can follow through all the steps and that they make sense to you.